Right, we have another really exciting calculus lesson. This time we're going to learn about how we can use algebra and some of the properties of algebra to evaluate limits rather than having to graph or make tables all the time. One thing to remember from our graphing lesson was sometimes the limit and the function value are the same. This top graph doesn't have any of those. The function value and the limits aren't always the same. But sometimes, like in this bottom red graph, right here at 0, we see that the limit is equal to the function value. And those kind of functions are what we call, or what your textbook calls, well-behaved functions. And that allows us to just use what's called direct substitution to find limits, and that makes this a really super easy process. So we talk about well-behaved functions and this idea of direct substitution. That literally means, here's our rule right here. So as you can see, you're taking the c value and you're plugging it into whatever the function is for the x value. Okay, well-behaved functions are anything that doesn't cause a division by 0 or doesn't have an even root, so square roots or fourth roots, sixth roots, those kind of things, of negative quantities. Those are the only two things in algebra that you are not allowed to do. And hopefully you remember those two. No division by 0, no even roots of negative quantities. Everything else can be evaluated using direct substitution. So we're going to look at a whole bunch of those things today. Like I said, your textbook calls them well-behaved functions, which is kind of funny. So our very basic limits, if we have the limit of just a constant value b as x approaches c, no matter what, that's going to be b. There's no x to plug c in for, so that first rule is just the limit of a constant is equal to the constant. Second rule there, the limit of x as x approaches c is equal to c. Again, we did a direct substitution where we plug whatever c value in for x. And the third one is the limit is of x to the nth power as x approaches c, so we get c to the n. It's all a direct substitution, taking that c value and plugging it in for x into the function. So if we evaluate some of these things using those properties, the first one here, the limit of 7 as x approaches 4, that's rule number 1, so that's just going to be 7. The second one, limit of x as x approaches negative 2, that is rule number 2, so we take negative 2, plug it in for x. That limit is negative 2. And the third one here on the right is rule number 3, so we take our 3, plug it in, we get 3 to the 5th, or whatever 3 to the 5th equals. Okay, some more in-depth properties are different ways that we can combine functions or kind of manipulate them a little bit, but as long as your functions f of x and g of x have limits and are the well-behaved kinds of functions, then direct substitution works as well. So number 1, if we have a scalar multiple, you just end up taking that multiple times whatever the limit of f of x was. So those were defined as L and K up there for f of x and g of x respectively. So we get b times L, whatever it is. If you're going to add two functions or subtract down here in rule number 2, you would just add or subtract the individual limits. Number 3, if you're going to multiply two functions, you multiply the two known limits. The quotient, as long as the function g, or the value g of c, does not equal 0, you can just divide those two. And the last one, a power, you just take the limit to the power. All of those, again, still work with direct substitution as well. So if you happen to forget some of these properties, sometimes you can just rely on direct substitution. So let's look at this. We have a graph this time, and we're going to find some limits from that. Notice that f is labeling the red function, and g is labeling the blue function. G is there, and f is up here. So when we're talking about the limit as x approaches -2 of f of x plus 5g of x, we might want to think about that as the limit as x approaches 2, or -2, sorry, f of x plus 5 times the limit x approaches -2 g of x. And then those individual limits, the limit of f and the limit of g, can be found from our graph. So that first one, limit of f as x approaches -2, -2 is right here. So the limit from the left and from the right looks like it's 1. So we have 1 plus 5 times, now the limit of g at -2, down here at -1. So simplify, 1 minus 5, we get a limit of -4. Just using those properties that we talked about on the last slide. So now we have a product. So what you're going to think about is that you're doing the limit as x approaches 1 of f of x times the limit as x approaches 1 of g of x, and you find those two values from the graph. So limit of f as we approach 1 is 2. Limit of g as we approach 1, well, from the left we get a -2. From the right we get -1. So that limit of g does not exist. And 2 times does not exist means does not exist.